Finally, we're going to use group theory to assess the optical absorption, meaning the we can judge if the optical absorption is possible from the information of the symmetry of molecular orbitals. So what we have to do is to understand that if the light absorption is possible or not is, as we talked about, that the transition integral is going to have a value or not, right? And as a similar problem, first we are going to study if the overlap of the orbitals are possible or not. And it can be assessed by analyzing the overlap integral like this. So two of the molecular orbitals are multiplied and integrated in space, and then you have to judge if the integral is going to have a value or not. And if overlap integral has a value, these two orbitals can make a molecular orbital. So that's one of the applications using the group theory. And the calculation or the assessment is quite easy and straightforward. It is by multiplying the F1 and F2 should have an A1 group. A1 group you could find in A1 group always in the index chart here. For in the C2b case, you have A1 group here. In C3b case, also A1. So in any group, you have A1 group of molecular symmetry. So what you have to do is by multiplying these two molecular orbitals, and then still they must be included in A1 group. And this one indicates the A1, you could notice that any symmetrical operation in a group lead to the index number is equal to 1. So it's a symmetrical operation. After symmetrical operation, it's going to be overlapped. So it's not going to change the sign. So even if you even if you make a symmetrical operation, they are kind of overlap, and that's the necessary condition to have a value after taking an integral. Okay. So let's check one of the example here is the orbital of NH3, which is categorized into the C3d orbital, right? And can Sn, so S orbital of N, nitrogen, make an orbital with S3, which is composed of the S orbital of B minus S orbital of C, or S1 is equal to S orbital of A and B and C. So which indicate that's like this. So this is ammonium molecules, and SAS, B, SC are the S orbitals of hydrogen, you can see. And SB minus SC means the phase difference of S orbital in the hydrogen. Okay. So what you have to do is here. Already kind of the categorize the S of nitrogen is the categorized A1. which must be confirmed for yourself. So please do it for yourself. And S1 is categorized into the A1, and S3 is categorized into the E orbitals. So, and what you have to do is first confirm the index values by using the index chart here. So A1 is 1, 1, 1, and E is 2, minus 1, 0. Okay. So what you have to do is Sn, just write the index values 1, 1, 1, and then S1 also included in the A1, so 1, 1, 1, and then just multiply each component of the index and 1, 1, 1. This is the index values for new molecular orbital by overlapping Sn and S1, which is again the same as the A1 category, meaning based on this, if the multiplied the molecular orbitals are categorized into A1, it's going to have the value of the integral. So you can make an orbital, new orbital. So can be made. On the other hand, Sn and S3 case. So this one's 1, 1, 1. In the case of S3 case, 2, minus 1, 0. So 2, minus 1, 0. So if you multiply this one, 2, minus 1, 0, which is E, categorized E, so not A1. So this cannot make an orbital. So no overlap as possible. And actually, after calculating this kind of calculation, you could understand that this is a kind of important result. The orbitals in the same symmetry can only make an orbital. So just remember this. This is kind of one of the important aspects of this. So